So this is the final video that I will show performing the analysis required in the IB Physics lab report. So far we've got our nice table here. We've got our graphs. This was the initial graph. Here's the second graph we produced. It wasn't linear. So then we tested for a consistent offset in all values of velocity average. And we found that when we subtracted a value from every v, it did produce a straight line, which tells us instantly, yes, there was a consistent offset, and its amount was 11 meters per second. So the relationship that we have, this is a power relationship because it was linearized by our log-log graph. So here's the relationship, the general form, right? Oops. D minus b equals k times I raised to the n power. That's the general form. Now, of course, our dependent variable is v. I'm going to take off the average now because the actual dependent variable is velocity, not average velocity. And I'm plugging in what I found the value of b to be. It was 11 meters per second equals k times I to the n. Now I have to find k and I have to find n, those constants, and plug them into my equation, and then I'll be finished with developing my equation, my function, my model. So many things we can call it. So here's how I find k. K equals 10 to the b, where b is the y-intercept on this graph. N equals m, where m is the slope of this graph. So k is going to be equal to 10 raised to the 0.6859. And I didn't get my caret in. 10 raised to the 0.6859. There's k. N is equal to m. Might as well just copy this straight from here. Control C and Control V. Okay, so I come over here and I replace k with 4.85168. What have I done? I missed the 7. And n I replace with 1.2877, like that. Okay. Now, how many digits should I show? How many sig figs should I show in these values of k and n? Well, the most sig figs we have in anything is 4, right? So why don't and the least that I have is 2. There's not really a sig fig rule you have to use, so I'm just going to show 3 sig figs in the middle there. Like that. Maybe I'll just show 2, since 2 is the least number, so I'll change this. And there's my function, right? That's my function. Oops, except that I have to change I, the independent variable, is mass, m. Okay? And that's it. That's the end. That's what I've derived. That's what I've developed. That's what I've discovered. This is the relationship between velocity and mass for whatever experiment it was that I conducted. Okay. Now, what we have to do is test this relationship. So I'm going to delete these other cells because we're done with those. You test this relationship by plotting v against m raised to the 1.3. So here's my last column that I need to add. It's m raised to the 1.3. And I'm going to center that, and I'm going to merge so that these are all 1 and make it centered. My box, there it is. So I do equals m raised to the 1.3, and I bring this all the way down, add a box, center. The final graph then, and let me move my equation, my function, right to here. And the final graph, I'm going to move this one down here, and I'll move this up. Move this down. I copied this graph. Remember, you do that by holding Control while you're dragging. And here I'm going to do average velocity. Whoops. Actually, it's average final versus mass to the 1.3. So I copy this over. And my units here are grams to the 1.3, right? Grams to the 1.3 power. Which means, what are the units for 4.9, this constant k? What are the units? Well, if I isolate the 4.9, I have something in meters per second divided by something with grams to the 1.3. So the units for 4.9 are meters per second per gram to the 1.3. See that? So now I've added in my units using dimensional analysis. And again, I said this is the left side of the equation, has units of meters per second. And then I'm dividing left and right by grams to the 1.3. And the units of k, 4.9, are meters per second per gram to the 1.3. So you want to go ahead and add in your appropriate units there. Now, the final thing then is this graph. So I'm going to take away error bars for now. We'll have to add them in again later. And instead of m, it's this. And I add a trend line to confirm. Yes, look at that. 4.7, that was pretty close. And my slope is 11, right? And that's pretty close to this. So this confirms the relationship here that I've written down. If you want, you can rewrite this using this value, 4.7, instead of 4.9. Now, I'm going to move this again. The final thing is to add error bars to this graph, right? If my mass is being raised to the 1.3 power, then 0.3, the uncertainty in mass, divided by that mass gives me the percentage uncertainty. So, oops. So now, what I've pasted in here are percentage uncertainty, so let's make it a percent. And good, we'll just round to the whole number. So this is percent uncertainty in mass. Percent uncertainty in mass. If I raise mass to the 1.3 power, then I have to take the percentage uncertainty and multiply it by 1.3. Equals, let me try this again. Oops, and it's the percentage uncertainty being multiplied. Again, write it as express it as a percentage. So what I've just got in this column now is the percent uncertainty in m raised to the 1.3 power. That means the absolute uncertainty in m to the 1.3 power. In other words, the absolute uncertainty in m raised to 1.3 is the percent uncertainty times the value. And let's give that less decimal places. How many should it have? 1. Because absolute uncertainty always has 1 sig fig. Okay, you don't need to show this column or this column in Excel. You could just not show it at all. What you need to have is this column in Excel. You don't need to show it to me. All you need to have is a sample calculation showing how you found one of these values, which means you show me this, this, and this. Right? You show me all of the things I've got in these cells. Show me this step, that calculation, show me this step, show me this step. So you can show those in the sample calculation, and then I never have to even see these values themselves. And that's okay. Now, I'm going to leave this in for now. The reason I found the absolute uncertainty in the mass raised to the 1.3 power is so I can add horizontal error bars, right? So go to Layout, Error Bars, more error bar options. Vertical are displayed in this pop-up box, this dialog box. The vertical error bars are the same as what they were before. We have custom specify value. Look, it's the same. This is still correct because I still have average final velocity on the y. But I need to change my horizontal error bars. Uh-oh, they're too small to see. So here's what I'm going to do. I'm going to add with percentage. And now they're really big. If that didn't work, I would just add some other thing, standard error. Now they're even bigger. So I can see them, I can click on them. More options. Horizontal is custom, right? That tells me, the horizontal error bars tell me the uncertainty in the mass to the 1.3. So it's custom, it's specify value. It's this. That's how much uncertainty there is in the mass to the 1.3. And likewise, it's this. And again, Excel instantly pairs this uncertainty, each value, with the appropriate data point. So now those are my error bars, but I have to go and fix my vertical error bars because those got messed up. So the value for these is what I have here. That's the uncertainty in delta V, in V average. And I hit close. So those are some kind of big error bars, right? Kind of big. Now you can show me this graph and then show me another graph with your max and min slopes drawn in, and that's perfectly fine. You can use Excel and be clever about how you draw those in, or you can go to under Layout, Shapes, click this arrow, right? The line, and just draw these in yourself. Just connect the appropriate error bars, and then again, you can change the outline color to black, or if you want to change it to red or something different. I'm just going to use black. And then I'm going to click on my graph again so that my chart tools pop up. Layout, picture, add a shape. And I'm going to add this to this. I'm going to make it black. And there we are. Now I have the max slope drawn in, the min slope, right? If you want to label those with text, you can go to Layout, Text Box, click M max, right? And then you highlight max, subscript. And then just control click and drag and change this to min for that one. So I've got them labeled. And then if I want, I can calculate them, show the calculation on my own, and then do equals. Oops, let me get this out of the subscript by going back, unselecting. Right, slope max is something. I don't know, I'm going to make this up. Let's say it's 5.1. And I calculate this, and I show my calculation in my report. I show this calculation. Or you can use Excel to find it for you. That's fine. Just make sure you state which you used. Did you calculate it yourself? If so, show the calculation. Otherwise, you can just show how you got Excel. Just show what Excel gives. And then I do the same thing. I show my min slope. Maybe it's 4.7. Right? And that's it. I'm done. That's my final graph. So this is what you need to include in your data analysis, right? Now, it's not labeled data analysis necessarily for IB physics. You can just call it data, raw data, and processing. But this is the basic process you go through to find the uncertainty in the slope from the min and max slopes, and to produce all the necessary graphs.